Good afternoon, everyone.
Good afternoon.
So, have you worked on this? No, you didn't have time for it, huh? Is it assignment? If you start assignment at last minute, that's what happens, okay? They give you answers. If you haven't worked on it, I can give you last lecture if you want to try it by yourself. Or I can give you now. Doesn't make any difference.
I just have a question. Which table do you look at for getting the value? Like, do you use the one, or do you use the one? The one online?
The same.
Are they? Because I know that they have a little bit like.
No, they're exactly the same.
Okay.
So you have an exam in 10 days. So you better figure out how to pay it. Yeah. So you want the answers now or next lecture? Now?
Yes.
Okay. All right, temperature for first case is minus 32.08, to 0. Internal is 8.6, and top is 8.7. It will be not be determined. Temperature will be minus 32.08, 12 factor 1. Equal is 0.1472. Enthalpy 236.8. Case 4, temperature is minus 32.8. Quality 0.793. Physical volume is 0.117363. Enthalpy is 190.38. Okay, Anna, Cyrus, Shalene. Let's start. Good. Shall we move on? Okay. In last lecture, we started reading properties of pure substances. Right? We basically started using tables, reading properties from those tables. Right? We explained. If I try to explain, it will take time for you to digest it. So please make sure you understand how to read tables. If you don't know how to read tables, you will have a hard time in exam 1. Okay? Let's make this clear. You cannot avoid the class or first exam if you don't know how to read tables. Okay? If you have any questions, know my office hours. You can come to my office hours or you can set a meeting. Right? You can email me 24/7. Right? Feel free. All right. If you don't have any questions, we will move to a new subject, right? Which is properties of ideal gases, right? All right. Properties of ideal gas. Gases. Okay. Ideal gas is basically a pure substance as well. But specifically in pure substances, we call in thermodynamics, they tend to change phases, right? Which we talked about. In compressed liquid up to superheated vapor. But when it comes to ideal gases, right? There are pure substances as well. They can consider it under the pure substance, but they tend to behave nicer, more stable, mostly in a gas form. Right? What is the most well-known common ideal gas? Air, right? Mostly in gas. Have you ever seen a liquid air? You can, but it's under extreme conditions. Remember that curve with a critical point? If you exceed that to extreme conditions in terms of temperature or pressure, you can achieve to compress any gas, or most of the gas, I would say, from gas form to liquid form, right? Nitrogen, oxygen, hydrogen, air, these are carbon dioxide, carbon monoxide, etc. But we have also liquid form of those gases, right? But they change under extreme conditions, which we will not cover in this class, okay? But you should know that it's blue. Okay? Let's define what ideal gas is. Ideal gas definition. Fluid or enough from its saturation curve that it is not likely to condense into the liquid phase in any process generally referred to as a gas. Okay? If the temperature is high enough and the pressure is low enough, we consider those to be an ideal gas. Right? And it is mentioned here, they're far away from a saturation dome. So they are not likely to change phase unless extreme conditions. What are those conditions? if a fluid is a gas and its temperature is double, right? Divided, so division, T divided by T critical, that critical point on a saturation curve, right? Every substance, pure substance, has its own critical point, critical temperature, critical pressure, etc. If this value is higher than 2, and for pressure 10 of the critical pressure. For an ideal gas, right, for pure substances, a couple lectures back, we said that we need some properties for us to work on the problems to find the other properties. When it comes to pure substances, we change its phase, right? We said we have a couple methods to find those properties. One was algebraic, which was complicated. We avoided it, right? We can use graphics, tables, right? And we said we're going to use tables because they're already calculated and ready for us. When it comes to ideal gas, since they behave nice and stable, there's an equation that you can use to find the properties of ideal gases. Right? There's an equation, temperature, pressure, specific volume or volume are related, okay? Which is well known, you know that as well, right? What is it? PV equals RT, right? So ideal gas, for an ideal gas, PV equals temperature equals a constant. And this constant is called gas constant. And it is given the symbol R. Each gas has a different value of R. Right? Universal gas constant. Okay. Equal numbers of molecules behave similarly. That yields, right, same value of gas constant. Called universal gas constant. R sub U. And R sub U is 8.314 kilojoules per kilogram Kelvin, or R sub U is 1,545. The pound force per pound mole degree Rankine, or R sub U equals 1.986 ETU per pound mole degree Rankine. What are the ideal gases we are going to cover in this class? Air, nitrogen, oxygen, carbon monoxide, carbon dioxide, and hydrogen. Okay. Relation between R and R sub U. A mole is an Avogadro's number of molecules, which is 6.022 times 10 to the 23 molecules per mole. Right? M, upper letter M, is the molar mass or molecular weight which equals the mass of a mole of a specific gas. For example, for carbon dioxide, what is the molecular weight of a carbon dioxide? 44 kilogram per kilomole. Okay. Therefore, R equals R sub U, universal gas constant, divided by the molecular weight. Right? Molecular weight is not a mass. Don't confuse them. The molecular weight. Combining the previous ideas, we may generate several versions of ideal gas equation. What? plus PV equals RT. Right? I know what V is. V equals total volume divided by mass. Right? If I substitute this back to state equation, right? PV equals mRT. All right. Now I know my gas constant equals universal gas constant divided by molecular weight. Right? And I also know N is what? Mole, right? Equals M divided by molecular weight. By using these two, I have another equation, P times V equals N RU times T. Okay. Now, other properties of an ideal gas. If you go back to our calculus, right? If I take a function, and if I call that function z, right? That z is a function of x and y. Right? Derivative of that z will be equal to right, dz partial derivative of z or partial derivative of x. The y is a constant. Plus times dv dx plus partial derivative of z y over y x dy. Okay? So it's from the chain rule, right? Substantial derivative by using the chain rule. If I apply this, the thermodynamic property by considering the state postulate. Internal energy U. For example, if we let internal energy equals, right? Internal energy, the function of temperature and specific volume. All right. If I take the substantial derivative of internal energy, the du will be equal to du or dt times dt plus du over dv p dv. Okay? Here, I'm gonna call one of these the constant, right? This one. I'm gonna call this C sub B. Okay? For convenience, I will call or we define, right? C sub V equals du over dt sub specific volume V. Okay. So this term C sub V is called specific heat at constant volume. Okay. If I take this and substitute back to my substantial derivative, Cv times dt, right, plus du over dv dv. Okay. If the fluid is an ideal gas, this term right here, du over dv of t equals 0. So all I have is, right, therefore, du equals Cv C sub V times dt. Right? What I have so far. For an ideal gas, from all these derivations and explanations, I can tell that for an ideal gas, internal energy is only a function of temperature, right? You can put a note on. So for finite changes of state, changes in internal energy may be determined by integrating the expression below, right? If du equals Cv dt, then du from state 1 to state 2 will be Cv dt, right? From state 1 to state 2. So from state 1 to state 2, okay, from first temperature to second temperature or final temperature, so we might state this. So this integration is easy if Cv constant. Considered to be constant. Right? What happens in that case? I take the Cv outside, right? Internal energy difference, B You take the CV outside, you care of the integral, right? T2 minus T1. Okay. Talk about enthalpy. Another example will be enthalpy. Enthalpy, if you let enthalpy equals, right, the temperature is a function of temperature and pressure, then a substantial derivative, the H, will be equal to, right, H over dt, P dt, plus H dP, P dP. Just like what I did for internal energy, right? I'm going to call first term, right, the constant variable. In this case, it will be C sub P. Okay? So call this guy right here C sub P. Okay? We define C sub P H dP sub P. And this guy over here is called specific heat at constant pressure. Then this expression here, dP dt plus dH over T dP for an ideal gas, right? If the fluid is an ideal gas, this guy right here, dH over dP equals to 0. Okay? So therefore, if I organize my expression, dH will be Cp dt. And the same thing, what we said for internal energy stays the same for an enthalpy, right? For an ideal gas, enthalpy is only a function of temperature. Okay. So for finite changes, for a finite changes of a state, changes in enthalpy may be determined by integrating expression delta H from state 1 to state 2, right? Integration Cp dt from state 1 to 2. Right. All right, for a constant specific heat, the constant pressure delta H from state 1 to state 2 will be equal to Cp times T2 minus T1. Let's keep it constant. Okay. Specific heat for an ideal gas. H equals U plus PV. We have defined it at the end of previous lecture, right? So, and I just define P V equals RT. So, if PV equals RT, H will be equal to U plus RT, right? I take the derivative of this, EH equals DU plus R dt. And I know that du equals C sub V dt and dH equals C sub V dt. So in this case, Cp dt will be equal to Cv dt plus R dt. If I get rid of the temperature, derivative of temperature, right? All I have is Cp equals Cv plus R. Any questions? Okay.
R in that equation is the specific gas constant.
Gas constant, not a specific constant.
It's the gas constant for a certain gas. Or
Right. There are two different things. Right? Gas constant is not a universal gas constant. Gas constant is R, universal gas constant is R sub U.
Okay.
Right? Universal gas constant is a constant, but R is not. R varies from gas to gas. It's an identical property. So, yes,
What was C sub R?
C sub R.
Yeah. Maybe that's misread that.
I wrote the C
It
sub
might
R.
have been C sub D.
Which one?
This is the last equation I wrote down. I think I just misread it. I thought it was
Oh, it's a V.
wrong. Okay.
All right. Ratio of specific heats. The parameter K equals Cp over Cv. And it's called the ratio of specific heats or isentropic constant. When an ideal gas undergoes a reversible adiabatic process, it will follow a line such as P times e to the power k as constant. This case will be P1, V1, P2, V2, case of K. Okay? The one we did for substance, pure substance, ultra process. Right? So for an ideal gas, it will reversible adiabatic process we will mention after first midterm, what reversible or what irreversible is or what is isentropic. Right? So in this case, we will just stop here without explanation of reversible adiabatic processes. Okay? So this is all you should know for now. We will cover all those after first exam. So K is also called isentropic constant, which is the ratio of specific heat, Cp over Cv. Okay? Okay. So you should have tables for ideal gases. If you go to table 820, table 820, you should bring your tables. You should bring your tables. Table 820. What you have here on table 820 is the ideal gas specific heats of different ideal gases. Right? Hydrogen, nitrogen, carbon monoxide, carbon dioxide, air, and oxygen. Okay? So for example, for an air, Cp value is a function of temperature, and Cv value, C sub V, C sub P, and K, ratio of specific heats are tabulated, right? You read those values from the table. Okay, we can go to table A20, read that, air, nitrogen, oxygen, hydrogen, carbon monoxide, and carbon dioxide. Okay. So we have another table for an ideal gas, properties of air, you have also nitrogen, oxygen, etc. For table A22, right? This is tabulated as a function of temperature as well. Okay? Table A22. Okay. I will mention this later. Okay? Hold it for now. Okay, let's move on. Variable specific heats. Okay, we just defined that expression for internal energy and enthalpy, specific enthalpy, right? dH equals Cp dt, du equals Cv dt. But that's the case when the Cv and Cp are constant. What happens? They are not constant. You can't take them out from the integral, so you have to take care of that part as well, right? So when Cv and Cp cannot be assumed to be constant, which is the case most of the time. We need to have Cv, the function of temperature, and Cp, the function of temperature. So in that case, to be able to carry out the integration shown above, right? This process adds additional complexity to the process. But as an engineer, we need to make things simpler so we can make it useful, right? Or if we are going to need these properties frequently, it is more convenient to perform the integration once and tabulate the results. U internal energy, the function of temperature, will be Cv dt from one reference point to any temperature. And enthalpy would be T reference to any temperature, Cp dt. So T reference, T ref stands for T reference, okay? And it's usually at absolute zero temperature. Okay. For delta U, right, integrate this, okay, from state 1 to state 2. T1, T2, okay, dV, dt equals dV dt minus dV dt. Okay. T reference to T1, T2, T reference to T1. And this is equal to 2 minus U T1. Okay. And same thing for entropy from state 1 to state 2. Dp dt equals dP dt minus dP dt for T reference T2, T reference to T1 equal to H T2 minus H T1. Let's go to table 822 now. So if you look at the table 822, a function of temperature, internal energy, enthalpy. Don't worry about these extra 3 columns. We're not there yet. We'll come back and explain in the future. Okay. So for the variable specific heat, right? CVCP changes as a function of temperature. And CVCP changes as a function of temperature, you can take it off from the input. So you have to take that part separately or as well as temperature as well as temperature. So enthalpy, right, and internal energy are tabulated by using these 2 integrations. Right? So once you have the temperature, you should be able to find the enthalpy and entropy. And once you don't have integral exact temperature shown here, okay, you do interpolation or extrapolation. Okay, clear? You know what interpolation, right? You use it for an assignment. You should. You haven't? Okay. Clear? Okay. So the processes, we have the same processes as we had in the previous lectures, right? To conduct the state, to heat, to work, and do some processes. And we had the same thing here for an ideal gas, nothing has changed, right? Instead of pure substances, we have ideal gas. So for an ideal gas, right? Let's start with the isometric process. Okay. Isometric. Process. on a PV diagram. What is P? Pressure. It's a unit, right? And make sure you put the unit. Is it bar? Is it kilopascal? What is it? Make sure you put the unit. Bar. PV diagram. V stands for specific volume or volume. In this case, specific volume. Put the unit. Right? From isometric process, this isometric process is specific constant volume, correct? But for state 1 and state 2, if I have state 1, let's say there's an expansion, right, from state 1 to state 2. The vertical lines, right, V2, constant V1, constant V2. In this case, V2 greater than V1, right? Right. Isobaric process. For an isobaric process, of an ideal gas, P equals constant. Therefore, work from state 1 to state 2, PdV, right, will be P V2 minus V1. Right? Combining with first law of thermodynamics, it's a specific word. Okay? I have to mention that. So, specific heat Q will be equal to internal energy change plus work. For U2 minus U1 plus P V2 minus V1. From the definition of an enthalpy, this would be equal to heat from state 1 to state 2 to be H2 minus H1, right? Okay. The PV diagram. For an isobaric process, constant P1, P2, constant pressure. In this case, P2, P1. Isothermal process. We can also observe that an isothermal process of an ideal gas follows a process line PV equals RT, right? Or PV will be constant. For constant PV, right? PV1, P1, P1, V1 equals P2, V2. In this case, work calculation, work from state 1 to state 2, from 1 to 2, P dV will be equal to dV R over V. For RT. So at RT dV over V. I forgot the T. So RT is constant. Right? So work from state 1 to state 2 will be RT natural log of V2 over V1. Or RT times natural log of P1 over P2. Pressure versus specific volume diagram. Isentropic, isothermal, or isentropic. Oh, we're in isothermal, right? Isothermal process. For state 1 and state 2. For state 1 will be synthetic curve. State 1 and state 2. For state 1, let's call this state 1, constant temperature, and this will be constant temperature 2. Here, P2, P1. We have one more process. Will be isentropic. Process. So when an ideal gas undergoes a reversible adiabatic process or isentropic process. it will follow the process. P times V to the power of K equals constant. P1 to the K equals P2 to the power of K. Work from state 1 to state 2. PDV, right, integration of PDV from state 1 to state 2. If you plug this into integration and take care of the terms we did in a couple lectures ago, right, you will end up like this: P2 V2 minus P1 V1 divided by 1 minus K. The PV diagram, reversible adiabatic process is shown. Looks like an isentropic, isothermal process, but it's steeper curve. Okay, it's steeper curve. Any questions? Okay. Any questions? Okay. This is all for today. If you have any questions, let me know. If you attended the lecture through Zoom, let me know you attended it, or you will be absent. Okay? So I will see you next lecture. Okay? Have a great weekend.